Hello, and welcome to our second lecture in the series where we talk about experimentation and active learning. In the first lecture, we briefly spoke about, we motivated the idea of using active learning, experimentation, or reinforcement learning in a broader data analytics setting, where we said these are some approaches that are fairly relevant when you don't have data. When data does not exist, or the data exists and it's not enough, or you have only partial data. In the first lecture, we also went into design of experiments and spoke about how perhaps an approach where you sequentially change one variable at a time need not be the best way to conduct an experiment. And we also spoke about something called orthogonal arrays, and specifically there we spoke about a form of experimentation called the full factorial design, where it's essentially a complete enumeration of a discrete input space, where even if you have continuous input variables, you break them into 1, 2, or maybe sometimes 3 discrete points, and you essentially do a complete enumeration, which means that every variable is set to every possible value it can be set to, with relation to every other variable being set to all their possibilities. So all the possible points in the input space are essentially looked at, and that was essentially looking at the design, meaning what points in the input space do you choose to experiment. In today's lecture, we'll briefly take just the full factorial, which is a very basic design, and talk about some approaches that are used in analyzing such an approach, such a design. So, jumping into the subject, in this slide, what we have is a full factorial design associated with 3 input variables, A, B, and C, and the idea here is that what we have is a full factorial design because A can take on 3 values, -1, 0, +1, and B can take on 2 values, and C can take on 2 values, just -1 and +1, and that gives you 12 combinations totally. And we have taken the output variable as Y. Now I've called them Y1, Y2, Y3, Y4 only because they are Y1, Y2, Y3, and Y4 are replicates. So it's the same core variable, but essentially you conduct the experiment at the settings, for instance, -1, -1, -1. You conduct that experiment 4 times. Again, it can be a parallel effort or a sequential effort, either way. What we mean by that is, when we say we conduct the experiment 4 times, you might have one experimental unit and you separately conduct the experiment 4 times on it, or you could have 4 experimental units and you might choose to parallelly try the same setting of -1, -1, -1 on those 4 different experimental units. But essentially, this is almost a setting where you conduct 48 separate experiments, and in design of experiments language, that's just called 48 trials or 48 runs, and these are essentially your results. These are your outputs. Okay, and the convenience of this is sometimes you can look at this raw data, or you can look at the average Y, and this is nothing but the average. For instance, for the average 80.75 comes from taking the average of these 4 numbers. So each row is averaged and it's represented, and those are the results that we have, and this is essentially what we look to analyze. Okay, so what is one way that you can take these results and arrive at a conclusion of what values A, B, and C should be set to, because that's kind of the goal. The goal is to figure out what to set A, B, and C to. I mean, to be accurate, one of the goals can be on to what values to set A, B, and C, such that you get the best Y. And here we're going to treat best as the highest value. Okay, so how should I set A, B, and C so I get the best Y? One approach is called the classical analysis. The idea behind classical analysis is to take each variable individually, each input variable individually, and ask the question, at what setting am I getting the best results? So A is set to -1, A is set to 0, and A is set to +1. So if I ask the question, what is my y on average when a is minus 1? What is my y on average when a is equal to 0? What is my y on average when a is equal to plus 1? And I look at these three numbers and I'll choose the value of a where my average y is the best. I will similarly do that for B and C, and I'll come up with a recommendation on that basis. So what does that look like for this data? It's a fairly straightforward calculation. When A is set to minus 1, you essentially get 81.81. So that just means you can think of it in many ways. You can think of it as the average of these data points right here, what I've circled, and the average of these data points, or you can think of it as the average of these data points, because ultimately each row comes from an average from that respective row, and the sizes are equal. But you can think of it either way. Either way, this is the average y when a is set to minus 1, and that's 81.8. And similarly, you get an average for 0, you get an average for plus 1, and so you would basically say, I like A at minus 1, it's giving me the best results. Similarly, you do it for B at minus 1 and B at plus 1. Now when you do it for B at minus 1 and B at plus 1, how do you take the average? It's the same principle, right? So you would, for instance, at B at minus 1, you would be interested in taking the average of these points, right? B is minus 1 at these points. So it would ultimately be the average of these points. So essentially that average would be B at minus 1, and that's 77.83. So you do the same process, and it's clear that A at minus 1 is the best, B at minus 1 is good because B at minus 1 is greater than B at plus 1, and C at plus 1 is good because that's better than C at minus 1. Okay, so that's essentially classical analysis, and it's a fairly heuristic approach, and it's like a first cut approach. Now that's one way of going about the analysis. Another approach is to take the best. The take the best essentially says, I'm going to look at that treatment combination which gave me the highest average y. So what would that be out here? So it looks like 85.75 is the highest average y, right? And that setting is, I believe, A111, and so we would essentially go with that recommendation. So take the best would have selected A is equal to 1, B is equal to 1, C is equal to plus 1. So here are two fairly contrasting approaches, and the question you need to ask yourself is, where would you want to use classical analysis, and where would you want to use take the best? And to answer that question, we need to answer that question in terms of, if you were to take a one factor at a time approach, right, what are two reasons that experiments, that particular approach fails, or for that matter, what is the two major difficulties with design of experiments? The two major difficulties are the following. One is that you could have some interactive effects between the input variables, which means the effect that an input variable will have on the output variable really depends on how some other input variable is set. Okay, so that's called an interactive effect. The other reason is that sometimes you get fooled, because yes, y is some function of A, B, and C, but on top of that, right, there is also some noise. So that noise could have given you results which you are erroneously interpreting, and you're essentially overfitting, and you're getting fooled. Now, the question is, under what circumstances would a classical analysis work? Under what circumstances would take the best work? And the quick answer is, a classical analysis essentially works really well in an environment of high error or noise. So when this when the noise, which is, so we said y is equal to f of A, B, and C, right? But it's also got this noise component, and when this noise component, although there could be no bias to this noise, so this noise could be something like it's normally distributed with mean 0 and standard deviation, some standard deviation, right? Then if sigma e is very high, and so it's a very noisy environment, then classical analysis would work quite well because it's averaging a lot of data points. Now, where it won't work well is when there is lots of interaction. So you need low interaction effects for classical analysis to work because it's just taking the average at A and average at B. In contrast, take the best would work only when there's very low error or noise. It would not work well when sigma e square is high, but because it just takes the best combination, it's almost like it doesn't care about the interaction. So high interactions work very well in its favor, and so you would use take the best there. Now, the reason we talked about these two heuristics is to really motivate the statistical way of doing things, which is this dichotomy that you see between high noise versus low noise, and fitting to any shape you want versus not being able to fit to any shape you want, has a lot to do with something you've seen before, which is the bias variance dichotomy, right? And this bias variance dichotomy is what you're seeing in these two extreme approaches. The statistical way can sometimes balance that out, and so the truth is almost any supervised learning algorithm could be fair game. The only context is that the data set is fairly small, but any data set, any supervised learning algorithm that does not require a very large data set, that requires a very small data set but can still give you meaningful results, could be a fair game. And in that regard, stepwise regression is usually popular in analyzing designed experiments. You start with the basic model that y is equal to a linear function of all the inputs A, B, and C, and then you also try to incorporate two-way interactions in the form of saying A times B, A times C, B times C, and you could even have a three-way interaction, A times B times C. And because your variables are coded to -1 and +1, just multiplying A and B as an input can have a meaningful interpretation. Okay. Now, one thing that can be said about this process of design of experiments is the way we've done it with full factorials and the way we've explained it makes it essentially a one-shot approach. It basically means you've decided even before you see any results the entire set of points that you want to look at the input space. So if you look at this, you've already decided. So each treatment combination is a point in the input space. You've already decided all the points and how many times you want to query each of these points even before you look at even one result. So it's ideal in some sense for a parallel deployment, but if you could do this sequentially, is there a better way of doing it, which is can you react to the data you're seeing to say, I want to query this point more because I'm less certain about this point or variable, versus saying, I'm very confident about something else, so I don't want to waste my resources in conducting experiments in a particular place. And that's primarily the motivation of sequential experimentation. This idea that you can conduct experiments sequentially, and that gives you an opportunity to react to the data. Now, in many ways, while sequential experimentation has been an effort from the statistics community, active learning essentially is the same core idea, and it's been motivated more from the machine learning community, and the context in which the problems are applied do sometimes differ as a result. Active learning is often seen as a semi-supervised learning approach, and understandably it's also called as optimal experimental design, because active learning is this process where the system sequentially chooses to query the design space and therefore be able to build knowledge on what we see and how it can be better understood. The key difference, especially in the typical context of application, is that while design of experiments often focuses a lot on this whole idea of starting with zero data, often active learning will start with this notion that there's some amount of data and it's not enough, and you might want to sequentially query the system to improve upon your understanding of the system itself. And so in many ways it's kind of seen as semi-supervised learning because there is an abundance of unsupervised learning data. It just means there's an abundance of states of the input space, and you sequentially get you choose points in the input state for which you really want to get answers and therefore get outputs for. And by doing that, the whole idea is that you can get away with much less data on the output space, and you can still come up with predictions that are meaningful. So what are some prominent strategies in the whole active learning framework? Is that, in a sense, all of these strategies that we're going to talk about now rely on one thing, right? It relies on evaluating how informative different points on the input space can be if you queried them and you got an answer. What we mean by queried is you choose a particular point in the input space and say, okay, can you please give me an output for that? And that now goes into your data set, where you can apply some kind of supervised learning approach to make sense of what you have. And the strategies that are involved with active learning can be broadly classified in these four. And this is an area of where there is active research, and so there might be some strategies that also fall that are new that might fall out of it, but these have been historically the more popular ones. So let's take a look at the first one, which is uncertainty sampling. Now, this is perhaps the most simplest and also therefore fairly common framework. And in this framework, essentially, the active learner chooses to query instances which it is least certain about how to classify or how to predict. So if it's a classification problem, it says, I'm going to ask questions about I'm going to choose points on which I want answers, on which I want you to give me an output, and I'm going to choose points where I am least certain currently. Given the information I already have, I am least certain about, if it's a classification problem of 0 and 1, I'm least certain about whether to classify it as 0 or 1. In those instances, I really want you to I want to conduct my experiment in that point where I'm least certain. Now, if you can also think of this as a regression problem where at a certain point in the input space you might have a prediction, but that prediction is not cast in stone, right? You have some kind of confidence bounds, you have some kind of bounds around that prediction. There's some amount of uncertainty associated with a particular predicted value, and you might choose to pick the point where your uncertainty is the highest. Another approach, also a fairly popular one, is this idea of query by committee. So let me just mark where we are. We finished this, and the second is query by committee. Query by committee approach essentially involves having a committee of different models which are all trained on the current data set. And when we say data set here, we are talking about the data set for which we have the outputs already, right? You have a data set with the outputs, and so you have some kind of supervised learner which is capable of interpreting the data, but you might have a committee of models which are all trained on the current data set, but they might represent competing hypotheses. Now, each of these members is now allowed to vote, right? And you basically choose to take you choose to get a data point from the input space where the committee members have the most disagreement, right? So think of it, one way to, one example that I've always kind of liked about this is it really maps onto a lot of ensemble methods, something that we saw earlier in this course. So if you had a set of methods, a set of supervised learning approaches, all trying to predict the same thing. So think of it as random forests where you have multiple trees trying to predict the same thing. So for a given input vector, each tree is not going to come up with the exact same class prediction, or it might not come up with the exact same prediction even if the output is a continuous variable. So this method simply says, let's go get an answer for a data point where the trees disagree most about what to classify it, or where there's the highest variance in the predicted value of the models. Okay. The next approach is expected model change. The idea behind expected model change is to see if we knew the label, right, of a particular data point, then which label of the input space, if we knew, would contribute to the greatest change in the current model we have based on the current data we have of the inputs and outputs. So you have some data on the inputs and outputs, and you basically extrapolate this to this broader question of asking the question saying, you could get data, you could get an output for any point in the input space. Which point would essentially lead to you making the largest change in the model? And the idea is to kind of query that point very specifically. Okay. The last two sets, which is the expected error reduction and variance reduction, use the following approaches. The approach is to basically say, with error reduction, right, the idea is there's some deviation of the prediction versus actual. So you can think of it as essentially the residuals in a regression case, and in every other case, right, whether it's bias or variance, for whatever reason you are unable to predict the exact value at a particular location. The question we need to ask ourselves is an answer to which point in the input design space could lead to the largest expected error reduction. Okay, and in that sense, it's fairly close to uncertainty sampling, but it's not just uncertainty sampling. It's the where it really differs from uncertainty sampling is uncertainty sampling asks this question about each data point in the input design space with respect to that data point. So I'll go to one data point in the design space and ask the question saying how much uncertainty is there in that point, right, in terms of my prediction at that point. Whereas expected error reduction does not talk about a single point. It talks about how if I got an answer to a question at a particular point, so I go to a particular point in the input design space and I query the oracle and I get an output. Now that output, if I now refit my supervised learning with this extra data point, there's going to be an overall reduction in my residuals across the board, because this new data point could change the entire regression line fit, right? Now this new regression line fit will create new residuals, and so I'm looking at the overall reduction in error between the data points and the fitted model. And so I choose to query that data point in the input space and get an output for that data point, which will lead to an overall reduction in error. Now, the variance reduction approach is a deviation from that. It's a deviation in that you don't look at the error between the fitted model and the data points, but you just look to reduce the overall variance in the output space. Okay. Now that is done probably because it's much easier to do this, but what the core idea here is that you have some variance associated with the outputs, and you can still continue to reduce generalization error indirectly by minimizing output variance. And that also can sometimes you do that because it's mathematically easier, and you can kind of get a closed form solution, and so that's essentially the core idea. Okay, so I hope this gives you some feel for experimentation and the whole idea of active learning, and at least some strategies that we could use in experimentation and active learning. Thank you.